Hey, physics students, welcome to another edition of Rapid Review for Honors Physics. Today our topic is continuation of work, power, and energy. Let's get down into it. Just as a quick review, in our last episode we learned definitions of work, power, and energy. You may have already done a lab involving energy loss. I put that in quotes because we will see soon that energy is not lost, it's just converted to another form. I'd like to also credit, and I will link to, the skate park simulation from PHET. This is a simulator series. I'll refer to those occasionally in my presentations. Our energy vocabulary has gotten quite expanded now. We know there's different kinds of energy, like mechanical energy and chemical and heat and so on. We also can split mechanical energy into two kinds, kinetic energy and potential. We have emphasized potential energy due to height as mgh, but there's also others. For example, a spring might be something that you might study. Okay, so that's a vocabulary review. And then I'll mention too, because I'm interested in mathematics, that the calculation for work is called a dot product or a scalar product. I mention that mostly because you'll start to see that as you continue your study of physics. It's something that pops up here and there as you're doing different kinds of study. So just a little fun fact. I want to remind you now, or mention here the definition of negative work. Negative work is when the force opposes the direction of motion. So in this example, if I take my angle between force and displacement to be more than 90 degrees, I'm starting to get in the way of motion. And so to an extreme, if the angle is 180 degrees, it's just completely negative work. I'm getting in the way. It's kind of an appropriate name, right? Like if I'm trying to move something and my friend is pushing the other way, pulling the other way, I'm like, dude, you're doing negative work, stop, right? So negative work means getting in the way of the displacement. And you can think of it in terms of components of force, just like we do for positive work. Moving on, I'd like to revisit the waiter problem. In one of the homeworks, we had a waiter carrying a tray. I will deliver this Progresso savory chicken and wild rice. They don't pay me for these advertisements. I'm going to deliver this to the table. I am the waiter. I am moving out of the kitchen. I want you to see this in three different parts, okay? First, my getting started, then my walking at constant speed, and then my coming to a stop. Okay, so here I go. Getting started, walking at constant speed, coming to a stop. Okay, now a lot has happened there. Let's analyze that in the pictures. If you draw a force diagram of getting started, that's, you have to read right to left here, the way I drew the diagram. Then you will see that I have an unbalanced force, which is my hand. It accelerates things, it's speeding up. My hand does positive work because the direction of the force of the hand is the same as the direction of the displacement. Now, in the second part of the motion, I'm moving at constant speed, and you'll notice there are no horizontal forces. This is difficult to imagine, and it's hard for us to accept, but it's true that if I'm walking across the room at constant speed with a tray in my hand, I am not applying any horizontal forces to the tray because the tray wants to move at constant speed. It doesn't need me to help it, right? So let's come back. The force diagram for walking at constant speed is as shown in the middle, and so no work is done. And then finally, as I slow down at part 3, as I slow down, the hand is doing negative work. As you can see, the direction of the force is opposite to the direction of the displacement. So I can do positive work, I can do negative work, and I can do no work at all if I'm carrying a tray across the room. It depends on whether I'm getting started, moving at constant speed, or slowing down to meet the guests at their table. Okay, here's another example of negative work. I'm going to come over here and slide this piece of timber tech along, right? You've seen this demonstration before. I am doing positive work and I'm moving at constant speed. How could this be? Well, here's what's happening. I'm applying a force and the force of friction is opposing it in equal amounts. So the force of friction is doing negative work because my displacement is moving, in this example, to the right. Okay? So that's an example of negative work. Who is doing the work? Well, I am doing positive work on the box, and I emphasize that again, right, or on the piece of timber tech on the table, and friction's doing negative work on the box. No net work is done on the box, right? I did work, so I did work. You can't say I didn't do work. The table did negative work, and if you net those all out, you'll see that no net work was done on the box. It's super important to keep track of these words. This word, this passive voice in English, no net work is done. You have to think about who might be applying and make sure that you have all of them accounted for. So net work, the net work done on an object is the sum of all work done on the object, and that's both positive and negative. Just like all net anything, you have to keep track of your positives and your negatives. Okay, here's another example. I'm going to lift an object at constant speed. I have this rock. I'm going to lift it at constant speed. All right, now, as I'm lifting it at constant speed, my hand is doing positive work, right? But if you look at the picture, you'll see that gravity is doing negative work, right? Because my displacement vector is going up. Or my velocity is going up, another way of saying that, right? So gravity does negative work while I do positive work, and no net work is done. No net work is done on the object. Finally, the work-energy principle. I have stated before, work and energy sort of kind of related. It's kind of difficult to explain. What we're going to do here is we're going to introduce this equation that the net work is the change in kinetic energy of an object or a system, right? So if I have positive work, I'm going to get a positive change in kinetic energy. That means the thing speeds up. If I have negative work, I'm going to get a negative change in kinetic energy. It means the thing must have slowed down. Let's check it out. Here's a couple examples. If I kick a soccer ball, I'm doing positive work because my foot and the ball are moving in the same direction as I am in contact with it, and the ball gains kinetic energy. It's a positive change in kinetic energy. Here's another one, sort of opposite, sliding to a stop. As this car skids to a stop, or as these two people sliding in their living room slide to a stop, the force of friction is going opposite to the direction of their displacement. So they are getting negative work done on the car or on the person, and therefore the person or the car is losing kinetic energy. You have a negative change in kinetic energy. Think also of a hockey puck going across a rink. It's the same thing. We analyzed that a couple episodes ago, right? Hockey puck moves. The force is opposite to the direction of motion or to the displacement. Okay? Here's another example, lifting at constant speed. If I lift my rock at constant speed, we saw this example, right? It turns out that no net work is done on the object. So there's no change in kinetic energy, right? I start out moving at some speed, and I continue moving at some speed, and that's the extent of the experiment as I'd like to visualize it here, right? We know, like from the waiter, there's the starting and there's the stopping, but while I am lifting it at constant speed, I am not changing the potential energy, and I am not changing the kinetic energy, and there is no net work happening because whatever I'm doing positive, gravity is doing negative. No change, okay? Likewise with the waiter, here, if I'm speeding up in step 1 and I'm going at constant speed in step 2 and I'm slowing down, I gain kinetic energy at the start. There's no change in the middle, and I lose kinetic energy at the end. Okay, so that's the way to revisit it in terms of kinetic energy and how it relates to work. Okay, so in summary, net work is the change in kinetic energy, and of course you know how to calculate that. You can just look at the 1/2 mv squared, final minus initial, just like any delta, right? Final minus initial. And that's how you do it. I would normally end here, but I want to add a few comments because this topic, as you start researching it in other sources and references, you'll see other words pop up. And I want to give you a look like behind the scenes into decisions I made when I presented this. Okay, so for this course, I'm analyzing the rock as an object. I'm not looking at the rock plus the earth as a system, right? You can look at it either way. I very intentionally selected my rock as my object. Here's another thing. I do not discuss, intentionally, I don't discuss fields. You'll see words as you research this, conservative fields, other kinds of fields, gravitational fields, electric fields. I don't get into that in this course, right? As you study more advanced things, that will be a handy way of looking at things. But if you come across that, you'll see if something I say in this course doesn't seem to exactly agree with something you hear in another course, it's because of that. Finally, you only get a brief mention here of thermodynamics. I would say when you get an opportunity to learn about thermodynamics, which you might get from a chemistry course maybe in high school, pay attention because it's useful stuff. Almost as good, I would say better than F equals ma. Really important knowledge about the universe. I have said enough for today. That's all I want to say today about work, power, and energy. I'll see you next time.